morning session, and that will be the Parallel Session 8 overview talk for interactions between space and planetary surfaces 2. And Larry Taylor, hi Larry, will be talking to us about an evaluation of space weather factors and lunar regolith simulants versus Apollo rocks and soils, a missing property.
Okay, before I get started today, I'd like to talk about the sessions that we have this afternoon, or this morning and this afternoon. And as you can see, we're talking about things that go all the way from minute little craters to large craters and all types of impacts. We also have a very interesting topic coming up right after this, and it's about lunar swirls. These are strange things that we discovered, and we didn't know too much about them, but now we know they had something to do with magnetic fields and with solar wind and particle size separation, things like that. They're really strange little critters on the moon, and I'd encourage you to come and see them, see more about them. This is a list of the celebrities that we're going to be talking today, and you can see we're going from all the way from the first part, which has to do with solar wind and magnetic fields and swirls and that, and then in the afternoon, Katie Burgess will be talking about some fantastic new discoveries with nanophase iron. We think it's only iron, but in fact, it may have different oxidation states than just neutral iron. And then we have other talks along there. The one I'm interested in particularly is the one by Andrew Jordan, the dielectric breakdown weathering. This is something I hadn't really anticipated too much of. I've been trying to think about weathering for quite a bit, but I sort of left that out. Today I'd like to talk about space weathering processes. And the space weathering processes are things that have come from all our studies of our best friend up there. Just think, this is our best friend. She has never turned her back on us, not once. Okay? I can't say that about anybody in this room. Okay? And so she's provided a paradigm for exploration, for planetary evolution. It's really been the thing. Lunar magma ocean was a big thing. And now everybody, terrestrial geologists, talk about magma oceans, magma oceans. I said, oh, you mean the lunar magma? What's that? They don't know where it came from. They don't realize that uridium anomaly came from our work on lunar rocks, trying to identify which rocks had a meteoritic component and didn't. That's where the KT boundary came from. So there's lots of things that come from the moon. Today I want to talk about space weathering on all airless bodies as given to us by our friendly moon. We saw this in early Apollo, and we saw a spectral reflectance of the soil, and we looked at it, and you can see there's almost nothing there. A little blip at 1 micron, maybe a little bit of olivine or something. But in fact, if you ground up the rock, boy, you really got a good spectrum. We couldn't figure out what's going on. And so this is what, John Adams and Tom McCord, the leaders in the field at that time. And this is our space weathering. And so we've been very disappointed that space weathering has really knocked the hell out of this whole paradigm that we had, that we're going to be able to determine all sorts of things. We're still able to do it, but it has taken 40 years to work out all the different problems that space weathering has put upon us. We're going to take the ages of space weathering you see here: micrometeorites, solar wind, different galactic cosmic ray particles, temperature, even gravity. People don't think of gravity. Gravity is a major factor. We'll talk about that when it comes to asteroids. But what I'm going to do is I'm going to take this, I'm going to extrapolate into the sun to Mercury and talk about the processes of space weathering on the moon as they apply on Mercury. Likewise, I'm going to go out to the asteroid belt and talk about the processes on the moon as they apply out there. All the same processes apply. It's just different degrees, depending upon what their position is relative to the sun. And of course, I won't forget about OSIRIS-REx. This is a big thing that's coming up, and it will be a definite plus for us in space weathering, but in general petrology, in asteroids in general. So I'll give you this slide. I've seen just about 1,000 times. It's my favorite slide. And it talks about space weathering. And it talks about the things that we think are obvious, the things on the right-hand side there, the weathering, the meteorites and micrometeorites. Yeah, smashing up rocks. We understand that sort of thing. But we had our terrestrial hats on, and we didn't understand what else could have possibly happened. But the fact is, we have things like radiation, we have solar wind. Now, what are these factors? Solar wind is like 95% protons. That's flying off the sun, about a third of the speed of light. They're coming in and they're hitting the moon at various angles, depending upon the effects of the magnetosphere of the Earth. But they're doing all sorts of things, implantation. Maybe this is what's creating our OH that we're seeing in the spectra from M-Cube and various missions now. The weathering that occurs from the meteorites and micrometeorites, we think of this, this coming in, and we can understand something smashing in, but the fact is, look at the velocities that we're talking about. We're not talking about little slow, we're talking about, just as Star Wars type stuff. 30, 70,000 kilometers per second, Mach 20, okay, Mach 50. These are tremendous velocities. These particles don't have a whole heck of a lot of size, of mass. We define micrometeorites as being less than 1 millimeter, but the fact is they have tremendous V-squared energy, and they do all sorts of stuff. Now, then the one thing I forgot, this is the missing thing, and this has just come up the last couple of years, and I'll point out a couple of papers, and I'll mention some of the major importances due to diurnal temperature change. Something we thought about during Apollo, but we sort of poo-pooed it and went away. Okay, and I'll talk about why we sort of missed the boat at that time. Now, just to show you this little micrometeorites, this is a 100 micron glass sphere, and you see the little itty bitty pits in here. And we call them these, we were very educated in those days, so we call them zap pits, okay? Really scientific term. But the fact is that there's a general axiom that the size of the projectile is about 1/10, 1/5 the diameter of the crater. So here you see a little tiny crater, 5 microns, and that means the particle is, we're getting down to now the resolution of an optical microscope. This is 1/100th the diameter of the hair on your head. Take the hair on your head and measure it with a micrometer, okay? We used to do that in the bar when I was a kid. The guy with the thickest hair was always the sexiest. So try measuring your hair sometime. Okay, now you're looking at these different velocities, and I've been talking about, and see here at Mercury, the velocity is almost twice what it is here. The average velocity of the micrometeorites that are impacting the Mercury. And obviously it's going to have a different effect than it has on Moon. But look at what it has in the asteroid belt. Not much at all. In Vesta, only 3-4 kilometers per second. In order to make it miles per hour, multiply it by 3,600, remember? Okay, so they're still quite high, but the fact is they're not near what they are at the Moon. And this was the major thing that Lindsay Keller did. He was a postdoc of Dave McKay's at JSC, and he showed these nanophase iron as a vapor deposited rim on almost all grains in a mature lunar soil. A fantastic discovery. We knew there was nanophase iron there. Now we call it in those days single domain iron because it had a specific size range, 3 to 33 nanometers. And then nano became sexy, so we said, okay, it's all nanophase iron. But the fact is that you look at these little particles here, this is courtesy of Sarah, and you'll see these particles are all about the same size in this TEM photo, and they are separated from each other. Each one has a little magnetic domain of its own. So this is a unique arrangement that God made for us, and we still are trying to figure out how to do it. Now, anyone who's ever taken geology, and we have a beginning course we call Rocks for Jocks, okay? And in that, we have the rock cycle, and we have rocks, sedimentary rocks, and they get ground up, become detrital sediment. They come down, and they form sedimentary rocks. And then they get metamorphosed, and they get squished and squeezed, and they change and everything. And finally, they get completely different rock. Then a little bit further metamorphosis, and you got liquid. They melt. And we got melt, and then we got igneous rocks. And then we got igneous rocks come, and they weather, and they form sedimentary rock. Oh, we've got a rock cycle. This is our soil cycle that we have for airless bodied regolith. Now you'll see to the left, you have large grain size. To the right, you have fine grain size. You have all this constant space weathering processing of the micrometeorites and solar wind and temperature and all these sort of things we're talking about. But see what happens. In the bottom, you see a selective comminution. That means it's becoming finer and finer. Things are being smashed up. Logical, we all know that. Okay? But then we have things that are happening. These little V-squared energy particles melt some of the soil. And as they melt them, they make agglutinates. And the agglutination sticks things together. And these agglutinates then have a the agglutinates then stick things together and they make things coarse. So we have two competing processes. Comminution here, just breaking up, and agglutination. But then in our agglutination process, we have this melting. And who's to control the temperature of this melting? It's not just 1200 C. That's what they need to melt lunar soil. The fact is, it could be 2000, 3000 degrees C. And that's where this vaporization comes in. With vaporization, you get dissociation, and you form all sorts of different iron zero, metallic iron, okay, elemental silica, in a vapor phase, which gets deposited. That's what Lindsay Keller and Dave McKay contributed. Okay? So we have this process going on, and it turns, now the fine stuff is, especially glass gets broken off into the fine particles. The fine particles of lunar soil contain much more nanophase iron than do the coarser particles, because all that little glass, that little fine coating on all those little grains is getting broken off and collected into the fine dust. Now, the thing I want to point out is that we always thought that solar wind was the thing that did all the nanophase iron. And it's logical. You can do it experimentally, real easy. A little bit of solar wind over oxide minerals, for example. Anything contains iron, be it iron silicate, iron oxide, iron sulfide, and you can reduce it to form metallic iron. So we thought this was Bob Housley's contribution in 1973. Now, it took us almost 3 years to figure out that that magnetic stuff in its soil was nanophase iron. It was magnetite, it was terrestrial hats. We got all confused. 3 years, can you imagine, way back then? We didn't have the instrumentation we have today. But Housley figured out in 1973, this nanophase iron was formed by hydrogen reduction due to the solar wind implantation in the soil. But I think that's a red herring, because this dissociation does the exact same thing. It gives you a reduction process. You start with vaporization, you actually boil, just like your spaghetti water boils. You boil the stuff, and different elements come off selectively. And they are then, depending upon the temperature, dissociated. And we had predicted that they would form various compounds like FeSi, FeSi2, etc. And then Mahesh Anand, one of my postdocs, I was showing him some samples, and I said, hey, look at this little grain. It looks like a little bit of metal, but it's pretty tarnished. And it turned out to be Fe2Si, proving what we had said. So there's this Fe2Si is in the lunar soil. So I named it after Bruce Hapke. Why Bruce? Bruce is a founder of our space weathering. He's a founder of remote sensing. He's like Tom McCord. He's one of the old people that really set the stage for everything. And in the early mid-70s, he had predicted a vaporization type of process that might go to this. He didn't know about this extreme or anything else. He tried some crude experiments and things, but the fact is it sort of fell through the cracks. And it wasn't until 20 years later then that Lindsay Keller picked it up. But the fact is, this is why we don't need hydrogen. And then we learned back in the 20th century. Now, I can say back in the 20th century. That's 15 years ago, okay? In the 20th century, we all knew that there could be no regolith on asteroids. That was just a given. I mean, people said that. And, it's like they said that rocks could never come off Mars until we proved that they did. And then they said, oh, yeah, why not? Of course. Well, we had this mission. And the near-Earth asteroid rendezvous with Shoemaker here on Eros, you can see the resolution in the upper left. We have a 2-meter boulder, okay? 1 meter per pixel. Okay, so we had things going on there that were just fantastic. Hayabusa mission was a fantastic, their Japanese mission. They went, look at it, it's all just a rubble pile. And then they found nanophase iron. Okay, so this nanophase iron is popping up all over the place. Now that means that this is a possible clue to space weathering. Then, not to be outdone, Sarah went to a howardite. Howardite is from Vesta. It's part of the eucrite diogenites. And howardite is basically a hunk of regolith that's been stuck together. So she looked at this regolith from Vesta, and what did she find? Nanophase iron. Why should be nanophase iron here? Then hardly any, the velocities of impact are very slow. Okay, then people have tried to duplicate things by laser impacting, and you notice that they have formed different size particles here. There's a whole serial array. So we've had various situations where they've made micrometeorite bombardments for laser ablation, to duplicate laser ablation, ion bombardment, duplicate radiation, and they've made native iron by various ways. However, in all the money, the millions that NASA has spent on SBIRs to make nanophase iron in lunar simulant, no one has duplicated the vapor deposited rims on lunar soil particles. So that means that a lot of this nanophase iron money that was spent is perhaps could be better spent someplace else. Now, to get into the temperature problem, here is temperature, and you'll look at the right-hand side, and you'll see in the early morning, and look at this little itty-bitty crack. See an itty-bitty crack right there in the morning. By the time in the afternoon, it's getting more stress, it gets larger. And this is, a concept of what we're doing. So these are some articles, if you ever wanted to read up about space weathering. The first one is by Chris Bennett, a student of Tom Orlando at Georgia State. It is neat. It says beaucoup references. I have never seen a paper with 764 references. Okay, 764. He combed the literature, not just Google and find out. I like Google. It's easy to use. I don't like it. Equals MC squared. Oh, J. Fred Muggs, 1992. Oh, okay. No, it doesn't go back. Okay. This is what he has done. Delbo is the one who really started this thing with thermal fatigue. Jamie Malero has this paper in 2015. She actually got her start with Chris McKay here on campus, on site, and she was working on this thermal processing of soil particles on Earth, and then she took it into a whole study on the elastic properties, thermoelastic properties in the modeling. You see, this is by Delbo up here, and what you're seeing is that on the x-axis we have a time, and on the y-axis we have size, and you'll see that a 10-centimeter rock should be completely gone in 3,000 years. That means that there should be no big rocks on the moon. This is at 1 AU, okay? But see, there seems to be a problem between modeling and realism. Just to remind you, these little asteroids that we're talking about, which are so important, are spinning like little tops. The average rotation is about 8 hours. They're just, hot, cold, hot, cold, hot, cold. Delta T is what's important. Now, here's something that Jamie Malero did. Oh boy. And she showed that during this daytime, you have a certain stress put on there by temperature, and then as nighttime comes, you have a compressional force, then you have daytime, and she modeled this for pyroxene, that's that little dark line. But then when you put two minerals together, it became much larger. This is a whole problem of how to model these things. The assumption is that on asteroids, the micrometeorites are hitting it so hard that the lack of gravity, real gravity, is driving off a lot of this soil. So they're thinking that it's the thermoelastic properties that are making the soils on asteroids. So the soils are going to be much finer. Just another way of looking at this is delta T over dt, to see how things are. Just nothing happens during full sun. Then temperature changes, gets cold, down, big compressional stress, then extensional stress. Just another way of looking at it. All these different properties have to be fed into these models. These properties, however, have been determined on a larger scales than the processes we're talking about. The major problem we have here is that the scale of observation of our processes is a megascale. The scale at which the process is actually occurring is a micro-atomic scale. So we have to do more of this atomic scale modeling and experimentation. This is what Jamie Malero will be doing at JPL. She just starts a postdoc there. So today I've talked about all this space weathering, all the different processes. I pointed out the moon and the major things we have at the moon, micrometeorites being the big thing. We looked at Mercury. Mercury has major solar wind. Now, why? Well, it's right close to the moon, but it's got a magnetic field, only 1/100th out of Earth. So the solar wind is actually driving the magnetic field into the ground. So we have major solar wind, 4 times more effective on Mercury. Micrometeorites, major, maybe up to 30 times more effective. Temperature, major. We're going to have a completely different soil there. A lot more glutinate, a lot more nanophase iron. This is an extension of what we know from the moon. We go the opposite direction. We have asteroids, and we look at them, and we see that we have solar wind. It's pretty minor. The particles, they're pretty small velocity, 3-4 kilometers, 5 kilometers per second. Temperature is going to be a major. They're spinning and spinning. The dT/dt is really going to be great for them, and they're going to have a fine grain size. So nanophase iron, probably not so much, but then again, we've seen it on several of the, or on an asteroid already from the Japanese Hayabusa. So today I've tried to emphasize that understanding space weathering is the key to remote sensing of airless bodies in the solar system. And I've tried to give you a bit of a flavor for the complexities that can exist. Modeling this is really a hard thing to do, and it's going to take a lot of very fine-grained observations, mainly high-resolution TEM type stuff, things that we couldn't have done 10 years ago, 20 years ago, or 40 years ago. So I thank you very much for your attention.
Great, thanks, Larry. I will take the privilege of being the moderator for this session and ask you the questions on everybody's mind, I'm sure, is how thick was your hair?
When I was younger, it was much thicker.